Okay, hey class, welcome to Physics 390 Class 9. In this video, we'll be looking at more of the uncertainty principle, and this comes from chapters 3.4 to 3.5 of our textbook. Specifically, we'll be looking at the general statistical interpretation for any observable. We'll be looking at the momentum space wave function. We'll be looking at the generalized uncertainty principle for any two operators. And finally, we'll look at the energy time uncertainty principle. So let's get started. Okay, so the general statistical interpretation for any of those observable. So if you measure an observable Q in a given quantum state, you will always get one of the eigenvalues of the operator Q hat associated with that observable Q. Okay, so you always get one of the eigenvalues. So just for example, if you're in the infinite square well, and you measure the energy, you're always going to get one of the allowed energy eigenvalues that go up as n squared. When you make a measurement, the system always collapses into one of those eigenfunctions, and you always get that one of those eigenvalues. So if the spectrum of the operator is discrete, okay, so if you have whether it's infinite or finite, the probability of getting the eigenvalue Qn associated with the eigenfunction Fn is Cn squared, okay, Cn squared, where Cn is the overlap of the eigenfunction with the state psi. And it basically tells us how much of that eigenstate is contained in the wave function psi. So again, with an example here for the infinite square well, if our wave function psi was the ground state of the infinite square well, then our wave function psi would just be f1 of x. So Cn would be 1, and Cn squared would be 1. So that means the probability of getting the ground state energy E1 would be 1, which makes sense. On the other hand, if we had a mixture of or a superposition of F1 and F2, that an equal mixture, then we would have an equal amount of F1 and F2 in psi. And so C1 squared would be 1 and C2 squared would be 2. So there'd be an equal chance of getting E1 and E2 when we measure the energy. Okay. On the other hand, if the spectrum of Q of the operator is continuous, the probability of getting a measurement, we have to specify the probability of getting it in a range, because for a continuous, there's technically zero probability of getting a particular real number out to many decimal places. So we specify the probability of getting it in a range, and it's equal to CZ squared DZ, where Z refers to the eigenvalue we can get, and DZ is a range of that eigenvalue, where CZ is the overlap of the eigenfunction FZ with psi. Okay, so again, just to take a definite example, suppose we're looking at position. Okay, so our operator is the position value, position x, then CZ is just going to be the position eigenstate F, which is x. Okay, so FZ would be x here, acting on or inner product with psi. But x psi is just the function written out as just the function psi of x. So when we take CZ squared DZ, that just becomes psi x squared dx, which is what we understand as the normal probability density of our wave function psi x. Okay, so when we take this to be position, we recover our interpretation of the probability density as psi x squared. Okay, so a couple neat properties here. Because the probability of getting some value for a measurement is 1, we have, for the discrete case, the sum over all possible probabilities, Cn squared, must be 1. Okay, so the sum over all these probabilities must be 1, because we must get some value for the measurement. For the continuous case, that would become an integral over all possible values of the measurement z of CZ squared, the probability density dz equal 1. And this is just like the normalization integral in the case that it's x. Okay, and then the expectation value is a weighted average. For the discrete case, the expectation will be the sum over the particular eigenvalues qn times the probability cn squared of getting each particular one. So we take the probability of getting each particular one multiplied by the value of each particular one, and we get the expectation value. For the continuous case, we get something similar. Rather than a sum, we have an integral. We have an integral over the eigenvalue z times cz squared dz, which would be the probability of getting a z in the interval between of width dz. So it's just the expectation value is a weighted average. Okay, and this isn't for a general operator Q. So not just we've taken the energy in the position, but it would also work for the momentum or later for the angular momentum and other any operator we can work with. Okay, so let's talk about the momentum space wave function, which turned out to be very useful. So let's look at what we were just talking about in terms of the momentum. So for momentum, the eigenstates are exponentials e to the I px over h bar with a normalization factor out in front. And so the weights, according to the formula, which we just saw, since momentum has a continuous spectrum of eigenvalues, it can take on, it's a real number. The weights would be Cp, which would be the inner product of Fp with psi. So if we take that as the inner product and expand that out, we're going to get the integral of this 1 over 2 square root of 2 pi h e to the IPH, well, complex conjugate, because it's on the left side, times psi. Okay. But this is actually nothing but a Fourier transform. It's the integral of the wave function psi times e to the minus IPX 1 over square root of 2 pi. And there's an h bar thrown in there, but we're not going to worry about that too much. It's still basically a Fourier transform. So these weights, these Cp, are so useful that we give them a special name and a special function. We call them the momentum space wave function, phi of p and t. And as we can see, C of p, and which is phi of p and t, we're just giving it that name, is the Fourier transform of the position wave function psi of x and t. This is the formula for the Fourier transform here. Okay, so let's take an example of why the momentum space wave function could be useful. So we ask the question, what's the probability of measuring the momentum of the delta function bound state? Psi x of t is a constant times this decaying exponential times the time dependence e to the minus it over h bar, where e for the bound state is given as this minus m alpha squared over 2 h bar squared, where alpha is the strength of the bound state. Okay, so you may remember this from the our previous video on delta functions. But anyway, the wave function in position space is this cusp with the exponentials on both sides, which is represented here. But now we're not interested in the probability of given positions. We're interested in the probability of measuring a momentum to be greater than this quantity m alpha over h bar. Okay, so how can we do that? Well, we can switch to the momentum space wave function. Okay, so we do that by taking using this formula here and finding the momentum space wave function, which would be the Fourier transform of the delta function bound state. So we have the 1 over square root of 2 pi h bar, this constant. We brought up the e to the minus it over h bar times the integral of this, the integral of e to the minus ipx over h bar times this x dependent term here. So all of these terms are in here. And if we do that integral, we get, it turns out, if you do that integral, you get the square root of 2 over pi p naught to the 3 halves over p squared plus p naught, p squared plus p naught squared times this time dependent exponential. Okay, so we've got the momentum space wave function here. How can we use that to find the probability of it being greater than P not equal M alpha over H bar? Well, we use the fact that just like for the position space wave function, we have where the probability of finding a given set of positions is the integral under the position space wave function times the under the curve of the psi squared. For the momentum space wave function, the probability of getting a range of momenta is the integral over that range of momenta. In this case, to be greater than P naught, that would be P naught to infinity of the square of the modulus squared of the momentum space wave function, dp. Okay, so we're going to take the modulus squared of this. So we're going to get a 2 over pi when we square it, a P naught cubed, the denominator will be squared. And then because we're taking the modulus squared, this will be multiplied by its complex conjugate, and the time-dependent exponential will cancel. So that's what we get here. This 2 over pi P naught cubed integral of P naught to infinity of 1 over P squared plus P naught squared squared. Okay, and then we just look up that integral, and we find turns out to be about, evaluating it in our favorite program, 0.0908, or just under 10%. Okay, so you can see the usefulness of the momentum space wave function. We can immediately find the probability of finding a given range of momenta when we measure it, when we measure the momentum. So it's a very useful thing, and we'll be using it more as we continue in this course, the momentum space wave function. All right, let's move on to the generalized uncertainty principle. So for any two operators A and B, which have the commutator, which remember is the difference between AB minus BA, which for operators is not necessarily 0. It is 0 for real numbers, but it's not 0 for operators always. So anyway, for those two operators A and B with this commutator, it can be shown that, and the proof is in the textbook, it takes several pages, that the variance of A times the variance of B is greater than or equal to this quantity, 1 over 2i times the expectation value of the commutator AB, the whole thing squared. Okay, so that looks a little mysterious, but it's called the generalized uncertainty principle, and it applies to any two operators A and B. Now, the uncertainty principle we looked at before applied to the position and momentum. So let's see if we can connect this one back to the position and momentum. So to connect this back to our first position momentum uncertainty principle, recall that the commutator of x and p is IH bar. Okay, so this, if we apply this to x and p, we'd have the variance of x times the variance of p is greater than or equal to, plugging in for the commutator as IH bar, 1 over 2i times IH bar. But that those i's cancel, so we get h bar over 2 squared. And then taking the square root of both sides, we have the standard deviation of x times the standard deviation of p is greater than or equal to h bar of 2. Okay, so so we've recovered our position momentum uncertainty principle by using the commutator of x and p in this more general, initially somewhat mysterious looking relationship, the generalized uncertainty principle. Okay, so just a couple comments about this, this generalized uncertainty principle. If two operators commute, and by commute we mean their commutator is 0, then looking at this expression, we would have sigma a squared, sigma b squared is greater than or equal to 0, since the side would be 0. So therefore, sigma a, sigma b would be greater than or equal to 0. And if that's the case, it actually can be shown that we can find a set of shared eigenfunctions for the two operators. Okay, so each operator would have its own set of eigenfunctions, but we can choose the eigenfunctions so that they're a common set of eigenfunctions, so that the associated quantities, the observable A and the observable B, can be known, each be known precisely at the same time. Okay, and that's something that can't be said of position and momentum, right? We can't know position and momentum at the same time because they don't commute, but they don't have A, B, X, P equals 0. But if two operators have X, A, B equals 0, then it turns out we can know them precisely at the same time. Just a couple examples of that. For a free particle, we can have any energy greater than 0. And for every energy, since the energy is kinetic energy, it's p squared over 2m. So we can have either a positive momentum or a negative momentum associated with every particular energy. So the states we would have would be momentum states moving to the left and to the right with each particular value of momentum. And then each of those momentum states would also be an energy eigenstate or energy eigenfunction with the energy p squared over 2m. Okay, so, and the energy and the momentum commute for the free particle because the energy is p squared over 2m and the momentum is p, and p squared commutes with p. Okay, another case which we'll see coming up fairly soon is the hydrogen atom case. And when we look at the hydrogen atom, the total energy E of the hydrogen atom can be shown, and we'll see this, to commute with the angular momentum, as well as the so-called Z component, or one component of the angular momentum. So those three observables, the energy, the angular momentum, and the Z component of the angular momentum, can all be known simultaneously at the same time. And if you take in chemistry, you may remember the hydrogen atom wave functions are labeled by N, L, and M. And those N, L, and M refer to the labels for the energy N, the angular momentum L, and the Z component of the angular momentum M. So, so that's the hydrogen atom. So that's another example of commuting operators. Another comment on this generalized uncertainty principle. Any two operators which don't commute, for example, energy and position in the harmonic oscillator, right? Because the energy in the harmonic oscillator is p squared over 2m plus 1/2 vx squared. So the p squared over 2m part, since it contains the momentum p, will not commute with the position x. Energy and position don't commute. And so the energy and position in the harmonic oscillator have an associated uncertainty principle, okay? So there would be a delta E, delta X must be greater than or equal to a certain quantity determined by the commutator between them. So the uncertainty principle is usually applied to position and momentum. That's the most common one, but it's not just position and momentum. In fact, it applies to any two operators which don't commute, and position and momentum are just a really good example. Okay. Okay, so hopefully that fills you in on the generalized uncertainty principle and how it relates to the uncertainty principle we've seen before. Okay, so finally, let's talk about the energy-time uncertainty relationship. So this one's interesting. The position momentum uncertainty principle is often written loosely. Instead of sigma x, sigma p is greater than or equal to h bar over 2, as delta x, delta p greater than or equal to h bar over 2, where delta x kind of stands for the standard deviation of x, okay? There's a similar energy time uncertainty relation, which is delta E, delta T is greater than or equal to h bar over 2. But it doesn't come from the generalized uncertainty principle, even though it looks almost the same, right? I mean, it's greater than or equal to h bar over 2. It looks very similar. The reason for that is that there's no time operator. And if you look at the general uncertainty principle, generalized uncertainty principle, it involves the commutator of two operators. So there'd have to be a commutator between an energy operator and a time operator. There is an energy operator, but there's no time operator, so that we can't derive this from the generalized uncertainty principle. Nevertheless, it can be derived, and I won't give the whole derivation here. I'll just sketch it out and try to give some insight into what's happening here with an example. So it can be shown, if you look in the textbook, it takes about a page to show that for the Hamiltonian H and an operator H and another operator Q, that the product of their standard deviations is greater than or equal to h bar over 2 times the time rate of change of the expectation value of Q. Okay, so that can be shown. So if we define delta E as the spread in energy, or the Hamiltonian H is the energy, so we're defining delta E as the standard deviation, and we define delta T as the standard deviation of Q over the rate of change of the expectation value of Q. So if we look at that, we plug in delta E for sigma H here, and then divide by the dq expectation value of Q dt, and then sigma Q over that dq dt is delta T. So that would become delta E delta T is greater than what's left here is just h bar over 2. So we get that relationship, delta E delta T is greater than or equal to h bar over 2. Where we've defined our delta T, again, it's not the spread of the, it's not the spread in the measurements of an observable like the energy. It's defined in terms of this spread of an operator and the rate of change of a given operator. So what does this mean? Well, delta T is really the time it takes for the system to undergo what we call a significant change. So if we look at this expression, sigma Q is the standard deviation of Q, and the denominator is how fast Q is changing. So if we take the standard deviation of Q and divide by the rate at which Q is changing, delta T would be the time it takes for the expectation value of Q to change by 1 standard deviation, which is a significant change in the system because the standard deviation is a significant chunk of the possible values of Q. So this is just a way to capture the idea of a time for a significant change, the time it takes for the system to change its expectation value of an operator Q, of a observable Q by 1 standard deviation. Okay, so that's what this delta T means, to undergo a significant change. So if we look at this uncertainty principle, if delta E is small, then since it has the product with delta T must be greater than or equal to h bar over 2, it must take a long time for the system to undergo a significant change. So delta T must be large. So it must take a long time for the system to undergo a significant change. And a very good example of this, if delta E is not even small but 0, which it is for a stationary state, that is an eigenstate of the Hamiltonian operator, then in that case, delta E would be 0 and delta T would have to be infinity. So in that case, the system cannot undergo a significant change. And that's because expectation values of all operators in energy eigenstates do not change in time. They're stationary states, so they don't change in time. Okay, so that's just giving a definite example to try to make this make more sense. Then if delta E is large, then the system can change more rapidly. Okay, so if delta E is large, delta T can be smaller and still satisfy the energy time uncertainty relationship. Okay, so let's look at an example. An important application, there are several applications of this, but an important application is to the decay of an unstable particle. So most particles are unstable. The electron and the proton and the neutron, fortunately, are pretty stable. but other particles with higher energies like muons and tau muons and mesons decay and have short lifetimes. So in the case of an unstable particle, the significant change would be the decay. So the delta T here would be the decay lifetime, which we call tau, okay? So if tau or delta T is very short, and for a particle called the delta particle, it's about 10 to the minus 23 seconds. So that thing lasts, man, barely any time at all, just a ridiculously small amount of time, like attoseconds or something. So it's gone just in a flash. Anyway, since delta T is so short, delta E would have to be fairly large to satisfy this equation here, the energy time uncertainty relationship. So the energy has a spread delta E, and it's not well defined. And then since mass, as you know from modern physics, is related to energy, the mass of the delta particle is not well defined. So when the mass is measured, or the mass is listed, if you look in a table, as 1232 plus or minus 120 MeV over c squared. So if you measure the mass of the delta particle, or you infer the mass from how it acts with other particles, you get a range of values. It doesn't have a well-defined mass. And that's because it's so unstable that delta T is small and delta E must be large. Therefore, there's a range of masses that the particle can have. And that's a relative uncertainty of about 10%. Okay, so that's kind of a cool application of the energy time uncertainty relationship. But again, a takeaway here is that although it looks like the position momentum energy uncertainty relation, it's actually comes from a different place, and T is not a operator. So it's a little bit of a different character, even though it looks the same. And but it has different applications, like this decay of an unstable particle, which I've just shown you. Okay, so just to recap quickly, we looked at the general statistical interpretation for a general operator. We found that it was the probability was proportional to the Cn squared or Cz squared, where that's the overlap between the wave function and the eigenstate of the particular operator. We looked at the momentum space wave function. We saw that it's another way to represent the state of a particle, which is very useful if you're looking at measurements of momentum. We looked at the generalized uncertainty principle. We saw that any two operators which don't commute have an uncertainty principle. And we saw how that connected with the position time uncertainty principle. And then finally, we looked at the energy time uncertainty relationship. Saw what we meant by the delta T as the time to undergo a significant change, and saw that an application of that where delta T, that significant change time, was very short. So delta E had to be big, and so delta M was big, and we had an uncertainty in mass of a decaying particle. Okay, all right, I hope this has been helpful. Thank you for your attention, and I will see you in class.